Okay, our title today is Using Initial Rates. Okay, and just get over the fact that it's pencil on the overhead. Okay, I would have you do it in class. Take 5 minutes to do it, but we're not going to be in our regular classroom tomorrow, and so, okay, this is just how it goes. Okay, using initial rates. So, we are going to look at a certain kind of data, initial rate data, and from that initial rate data, there's going to be some things that we want to determine about a specific chemical reaction. Okay, so here is the reaction that we're talking about, and I'm going to say it, and there's nothing here that's foreign to you, so between the faded pencil and what I'm saying, you should be able to do this. In terms of the net ionic, we have ammonium ion plus nitrite ion react to give us 1 mole of N2 gas and 2 moles of water. Alright, now the next thing I'm going to have you do, so that this isn't a movie that takes forever, is I want you to pause right now, and I want you to copy down this data. Okay, so pause the movie and copy down this data. Okay, and now what you're going to do with this data, you guys, is you are going to determine the order for each reactant, determine the rate law for the reaction, determine the overall reaction order, and determine the value of the rate constant K. Pause, copy, because I'm going back up. Alright, now, the order of each reactant. I'm going to show you a mathematical way of doing this on the board, you guys. But for now, let's just look at this data. Okay, so the order of the reactant, if you can remember, refers to what happens as you change the concentration of that reactant. How does it affect the overall rate of the reaction? Okay, so here we've got the initial concentrations of ammonium in 1, 2, 3 different experiments, and the initial concentrations of nitrite, and then we've got the initial rate in moles per liter second. So as soon as the reaction starts, they measure the rate of the reaction. Okay, so this is one set of data that you might be given and then asked to find the rate law for this reaction and other things like I have listed at the bottom. Okay, now, in this case, you guys, really, all we need to do is look at this data, and we are going to be able to figure this out, the order for each reactant. But I'm still going to show you a different way of doing it so that if you get a context that it's not easy to see it from the data, you're going to be able to do it. Okay, so let's remember now a zero order reactant. If you change the concentration of that reactant, it does nothing to the rate. A first order reactant, if you double the concentration, it doubles the rate. And a second order reactant, if you double the concentration, it quadruples the rate. Okay, so let's just look at these. Okay, so let's compare experiment 1 and experiment 2. So we only can look at one reactant at a time. So that means that we are going to look at these two to determine the order of nitrite in this reaction. The concentration of ammonium stays the same. It is the concentration of nitrite that's changing. So that's what's going to have the effect on the overall rate. So, I'm looking for 2 experiments where ammonium stays the same, nitrite changes, and that's this. So I've kept this the same. What has happened to the concentration of the nitrite? it's doubled, right? Between these two experiments. Okay, if we double the concentration of nitrite and keep the ammonium constant, what happens to the rate? The rate doubles as well. And so we can deduce from that the order of nitrite in this reaction is 1. It's a first order reactant. On the other hand, if we look at experiment 2 and 3, the nitrite stays the same, so it is not a variable, right? It's staying the same. We double the concentration of the ammonium, and what happens to the rate of the reaction? It doubles. And so what can we say about the order of ammonium as a reactant? It as well is a first order reactant. Okay, so we know that just from looking at the data, but still I'm going to show you how to do it mathematically. Okay, so this is nice, neat, lovely data. It's not always going to be that way, you guys. So sometimes you can look and you can figure it out, and sometimes you can't. And that's the reason why I'm going to go through a very lengthy mathematical process now to show you how to determine it. Okay, whenever I do kinetics problems, I always begin with the general form of the rate law. And so, the general form of the rate law in this particular example, okay, is rate equals K. Okay, and you had this in your notes yesterday. Okay, in its simplest form, rate equals K times the concentration of our reactants. And so we've got ammonium, NH4+, and that's we're going to say that's to the nth power. We've got to figure this out, even though we did already by just looking at the data, but we're still going to do it. And nitrite. So all of your reactants, you guys, and this is to the nth. And these are unknowns, okay? We don't know what those are yet. Well, we do, but just pretend like we don't. Okay, so I always begin with writing the general form of the rate law. No matter what my data looks like, doesn't matter. Okay, with all of my reactants in here. Now, most of the time, you guys, it's 1 or 2 reactants. Very rarely will there be a third reactant, but it does happen sometimes. Most of the time, it's just a hydrogen ion. It's just a proton, if there is going to be 3. Okay, so what I am going to do, you guys, is I am going to begin to solve for M. Okay, because my first question is determine the order of each reactant. I need to find M and N. So, I'm going to solve for M. Solve for M. Okay, and so what I'm going to do is I'm going to look for the 2 experiments where ammonium is kept constant and nitrite changes. And we know that that is experiment 1 and 2. So we're going to use experiment 1 and 2 to do this mathematically. And so this is how we're going to do it. We are going to use number 2 over number 1. Because these are the 2 experiments where the nitrite is changing and the ammonium is staying the same. Okay, so ammonium is not our variable. Nitrite is our variable. Okay, and so then you guys, what we're going to do is we're just going to fill in with the rate law. So then we're going to say, okay, the rate of experiment number 2 was 2.70 times 10 to the minus 7th. And the rate for experiment 1 is 1.35 times 10 to the minus 7th. Okay, and I'm going to do this, you guys, I'm going to do this down here, and I'm going to fill in. So I'm going to take away that equal sign because you really don't need it. It's just going to confuse us. Okay, so now I'm going to fill in everything for experiment number 2, and that is K, and my ammonium concentration in that case, you guys, was 0.1 molar. I'm not even going to put in, I'm not going to put that in. To the nth, right? Just filled in my ammonium. And my nitrite in that case was what? 0.01. 0.01 molar to the nth. Okay. Now I'm going to do exactly the same thing for experiment number 1. Right? So it is K. Concentration of ammonia is 0.1 molar to the nth. Concentration of nitrite is 0.005 molar to the nth. Okay, so now you guys, what's going to end up happening is that cancels, and all of those things cancel. And that leaves me with 2.7 times 10 to the minus 7 divided by 1.35 times 10 to the minus 7 gives me 2. 0.01 divided by 0.005 is going to be 2 to the nth. Okay, so can we solve for m? Yes, we can. What is the value of m? It's 1. So m is equal to 1. So that is the order of nitrite. Now we need to do the same thing with ammonium. But instead of it being experiment number 1 and number 2, which ones are we going to use? We're going to use experiments 3 and 2, because in 3 and 2, the nitrite stays the same, and the ammonium varies. So, let's see. So let's just pull it all down. The rate for experiment number 3 was what? 5.40. And the rate for experiment number 2 is 2.7 times 10 to the minus 7. Okay, and now I'm just going to pull down my data. So experiment number 3, K. My concentration of ammonium in experiment number 3 is 0.200 molar. And then I have, and that's to the nth. And then for nitrite, it is, well, it must be the same as it is for number 2. And that was 0.01 molar. And that is to the nth. Alright. And now we're going to bring it down for experiment number 2. So K, we still don't know what it is. And it is 0.100 molar to the nth. And the nitrite in experiment number 2 is 0.01 molar to the nth. Okay, so all of this can cancel. This cancels. This equals what? 2. Okay, 0.2 divided by 0.1 is 2 to the nth. And no, wrong, sorry. with respect to ammonium is first order. So ammonium is a first order reactant. Great. So now we know the orders of both reactants. We know what happens when they change their concentration and how the change in their concentration changes the rate, affects the rate of the reaction. Okay, so what are the other things that we need to do? We need to write the rate law for the reaction. So now we know the identity of N and M. We can write the actual rate law. Because we don't want those variables there. So the actual rate law itself is going to be rate equals K times NH for ammonium to the first nitrite to the first. But you know what? We don't ever write that. Because it's just itself. So there's no reason. If it's a first order reactant, you don't have to write the exponent. Because we know that if there's nothing there, that means it's a first order reactant. Okay, so this is the rate law for the reaction. Okay, what is the next thing we need to do? We need to determine the overall reaction order. Okay, you guys, so that's the rate law. Okay, so the overall reaction order. So in this case, you guys, that is going to be N plus M. So really, to get the overall order of the reaction, you add together all of those exponents. And in this case, you guys, it's going to be 1 plus 1. So that means that this reaction is second order overall. Second order overall. And the last thing we need to do is we need to determine the value of K, keeping in mind that as long as temperature and pressure stay constant, this is an actual rate constant, right? The value of K will always be the same. But if we change the temperature on this thing, then that value of K that we're going to calculate right now goes out the door, and we have to determine a new value for the rate constant based on the new temperature that we're doing it at. Okay, so when we are determining the value of the rate constant K, you guys, basically all we need to do is we can use any of the experiments that were given in our data. We can use experiment 1, 2, or 3. Now that we know the now that we know the rate, we know the concentrations, and we also know the order of each reactants, now we can just plug into the rate law to get the value of K, right? So we're just going to rearrange this thing and plug in information. So which one did I use to do? That's the data I used. It should not matter which one you use. The rate for that is 1.35 times 10 to the minus 7th moles per liter second. Is equal to K times the concentration of ammonium, and that's to the first power, but we really don't even need to write it, and the concentration of nitrite, also to the first power, but I don't need to write it. And then, you guys, I'm just going to solve for k, right? So I'm going to multiply these two together, and then I'm going to divide both sides by that product, and that's going to give me my value for k, which is 2.7 times 10 to the 4th minus 4th, sorry, liters per mole second. Okay, the units for K. I'm not even going to go there yet in terms of how do we determine the units for K. We will do it before the chapter is over, but right now, you guys, really all I want you to concentrate on is the numbers and how do we manipulate the numbers. And then once we're real comfortable with manipulating the numbers in various contexts, then we're going to tackle the units for K. Okay, so in this case, because they're not the same, it depends on the rate law, how many reactants we have, what their order is, all kinds of things we have to take into account to determine the units for K. And it's just going to mind boggle you at this point. There's no reason to do it. But we will eventually. So it's fine for today, you guys. It's 2.7 times 10 to the minus 4th liter per mole second. And that is K. All right, so now that we've got the rate constant, and we know the rate law, now look at all the things we can do. We can say, well, if I want this particular rate, and I've got this concentration of ammonium, what concentration of nitrite do I need to have in order to get that particular rate? Or if I have this concentration of ammonium and this concentration of nitrite, whatever those hypothetical things are, and we know the value of K, then we know what the rate of the reaction is going to be. So the rate law is handy, right, because we can do all kinds of predictions once we get the rate law written. And the rate law also tells us very interesting things about how the reaction proceeds, but we'll get there eventually. Not yet. Okay, that's all.